Okay, thanks very much. It's a real pleasure to be here at this very interesting meeting in this beautiful place. So thanks to Maciek and Gediminas for the invitation. I'm enjoying it a lot and look forward to the rest of the sessions. So what I'm going to talk about is some theoretical work concerning the topology of one-dimensional quantum systems that are far from equilibrium. This is work that has been carried out over the last 6 to 9 months, and it's all the result of work of Max McGinley, who's a very talented PhD student working with me in Cambridge. So the starting point is topological invariance, and we're all very familiar with the existence of topological invariance from thinking about, say, closed surfaces in 3 dimensions, where we know that spheres cannot be smoothly deformed into toruses or two-hole toruses as characterized by the genus. And this is beautifully captured by the Gauss-Bonnet theorem, which says that even if, as you deform this system, the local curvature can change continuously, if you integrate it over the whole surface and divide by 2 pi, you get an integer related to this genus. So you get this connection between something which is locally varying, but its global property is integer. And as many of you know, Thaulos and co-workers showed that this concept can be extended to the case of energy bands for electrons moving in 2 dimensions, where one can, the integer topological invariant is referred to as the Chern number in modern parlance, and it's related to an integral of some curvature, which is the Berry curvature, defined by the block wave functions and how they twist in momentum space as you move over the Brillouin zone. So this is a topological invariant in the same sense as this, in that this integer cannot change if you smoothly deform the energy band, that smoothly change these block wave functions. And smooth in this case means that the energy bands don't touch each other, so there's a uniquely defined block energy state at each point in K-space. And it also has clear physical consequences, notably that even though if you fill this band with fermions, it's a bulk insulator, it has metallic surface states, which in this case are chiral. They flow one way around the edge of the 2D system. So this has been known for a long time, but more recently, a decade or so ago, it was understood that this is part of a much more general picture related to so-called topological insulators and superconductors, and these generalizations arise whenever you impose additional symmetries. So rather than saying you let the Hamiltonian be deformed in any way, you say that you deform the Hamiltonian only within a certain class or of symmetry, so you would preserve the symmetry. And once you do this, you get so-called symmetry-protected topological phases, insulators or superconductors. The famous example is if you use time reversal symmetry, which is natural in the solid state. If you have a non-magnetic material and no magnetic field, then it turns out that you get a bulk insulator also in 3 dimensions, but with metallic surfaces, metallic 2D surfaces. And many other models that were understood before turn out to fall into that category. One that I'll touch on again later is the Su-Schrieffer-Heeger model, just a tight binding model of hopping between lattice sites. So in the unit cell contains 2 lattice sites, and therefore we'll get a 2-band model. And you have hoppings J prime and J between say strong and weak bonds as you go along the lattice. And this, if we work in if you write down the Hamiltonian that describes the energy bands in this 2-state system, then it takes a form shown here in the site basis, and this has what's known as a chiral or a sublattice symmetry, namely that it anti-commutes with one of the Pauli matrices, essentially arising from the fact that there are no terms on the diagonal, that it's only off-diagonal hopping. And now, in the context of topological insulators, one understands that this, if you fill the lowest band, it's a 1D band insulator, but there are gapless edge modes if it's in a topological phase. So there's been a lot of understanding of this, a lot of progress also in cold atoms and photonics outside of solid-state systems. What I want to talk about in the talk today is one aspect that arises in these artificial systems, in particular in cold atoms, where one can imagine changing the band topology dynamically. So you can imagine at a given time having some Hamiltonian where the lowest band has, say, trivial topological index, nu equals 0 if we're thinking about Chern numbers, which is what I called nu before. Then, as time evolves, you change the Hamiltonian in such a way that the bands, at some point, they have to touch in order to change the topology, but then we get some new topological band afterwards. And the question, so this one can readily do in cold atom experiments, and the questions one can ask are what consequences does this have for the topology of the system? One might be interested in preparing topological states, starting in the ground state of one Hamiltonian and trying to turn it into a state which has got non-zero topology. But notice that because of this band closing, the system is necessarily non-adiabatic. You're not protected by any gap at some point in the procedure. So the system will always be excited to some extent, and so one also may want to think about what topology means when the system is out of equilibrium. It's not just the ground state of a system or adiabatically connected to the ground state of a system. So these are the sorts of questions that we're thinking about. So, there's been quite a lot of studies already done in this area. Most of them have focused on the dynamics of this Chern insulator case. That's the 2D system with the Chern number that I introduced before. And let's imagine, for example, that we have a quench in that setting, where we start in the ground state of one Hamiltonian. Perhaps the ground state has 0 Chern number, and then we quench to a final Hamiltonian HF, so at some point in between, the gap had to close, and then time evolve under this Hamiltonian. So what happens there? And well, what one can do is just compute for non-interacting free fermions, one can compute how the block states change as a function of time, because now, whatever, at each k point, you start at the occupied state was some uk at time t equals 0, but now it evolves under some final Hamiltonian HF, for which it's no longer an eigenstate, and so there's some time-varying block wave function at each point in k-space. Now, this diagram is not very accurate, because really at a given k point at these later times, there's some coherent superposition of the particle being in the ground state and the upper state, and there's some oscillation between these governed by this Hamiltonian. But you can take these wave functions and compute the Berry curvature associated with them, and then from the Berry curvature take its integral and ask what the Chern number is, and what you find is that the Chern number stays the same. There's no change in the Chern number from what you had at time t equals 0. And so this may seem striking, because it's now the system is subject to a different Hamiltonian, but on another level it's very natural, because after all you had a topological invariant. You had some, your initial state defines some state of the block wave vectors. The time evolution is just some deformation of those states, and as long as that is smooth in k-space, then it won't introduce any singularities, and so whatever topological invariant you had to start with is going to stay the same at later times, albeit if these wave functions could get quite complicated and could change quickly in k-space. Nevertheless, the fact that you had this thing as a topological invariant is manifest by the fact that it won't change when you make these smooth deformations of the block wave functions. So what does that mean in practice? Well, it means that formally there's an obstruction to preparing a state with a different Chern number from the state that you started from. Although if you go slowly enough in finite system, then these deviations can be small enough that it shouldn't matter, but formally you haven't gone into the state with a different Chern number. Indeed, this has been explored experimentally in beautiful work from Christoph Weitenberg's group, where they, in a two-band model on a honeycomb lattice, they essentially mapped out what the block wave functions were at all points in the Brillouin zone, from which they could construct the Berry curvature and show that the total integral remained 0. It hadn't changed under the time evolution. There's another very nice idea that will be covered in the next talk, I believe, which is that you can nevertheless, even though the Chern number hasn't changed, you can find out information about the topology of the final Hamiltonian by looking at the time evolution of the block states, not just in k-space, but so also in time. So you have this three-dimensional space of how the wave functions are changing both in momentum k and in time, and from that one can deduce information about the final state Hamiltonian. I'm not going to go into that in this discussion. What I want to focus on is what's different when we go from this Chern number case to the symmetry-protected topological classes, the ones that I said generalize the Chern number to lots of different dimensions and other symmetry classes. What's different in that case from what I've described so far? So that's going to be my main focus, and really it's just going to be talking about what replaces this conservation of the Chern number. So, okay, so to discuss this, I'll think about one-dimensional quantum systems of non-interacting fermions, although one can also ask the question for interacting systems and for higher dimension, but I'm going to focus on this. And this is convenient because here in one dimension we can construct all topological invariants from this quantity which unfortunately we're labeling here the Chern-Simons one-dimensional Chern-Simons form invariant. It's the integral of the, it's the Berry phase as you go across the Brillouin zone. So this is the Berry phase across the Brillouin zone divided by 2 pi, or it's the Zach phase. So this is just a notation for the Zach phase divided by 2 pi. So from this, this is what one can use to construct the topological invariance in 1D, but it's rather different from the Chern number case. The Chern number, there's an integral which whatever smooth function you put in would always give you an integer. Here, this integral doesn't necessarily give you an integer. It only gives you an integer or a half integer. It's only quantized if there's some symmetry. And so this just reflects the fact that in one dimension, the topological invariants only arise if there is a symmetry. So you have to have some symmetry protecting the state in order to get some topological invariants. But whenever you know what the symmetries are, you can construct those invariants from this integral. So the example that I mentioned before and that I say again just to emphasize is this SSH model where, as I said, there's this chiral symmetry, essentially that the only couplings here are in X and Y. There's no term coupling to sigma Z. And so one can write parameterize the Hamiltonian as this complex number, a magnitude and a phase of this complex number, hx plus I hy. And if you go through the maths and work out what this CS1 is for the lowest band of this model, you'll find that it's a half of this number, which is how much this phase phi k changes as you go across the Brillouin zone. So this is an integer. And so essentially it counts how many times this quantity wraps around the origin as you move from across the Brillouin zone from minus pi over a to pi over a. So a non-topological phase is like this blue circle, which doesn't encircle the origin, so this winding number is 0. The topological phase is one that encircles the origin. This winding number is 1, and the CS1 is is 1/2, and it's fixed. And so this is our topological invariant, which can't change unless you slide this over here, but then at that point the magnitude of h vanishes, so the gap has collapsed, and so that's consistent with this topological transition. So the question, one natural question is this topological invariant preserved out of equilibrium? And as I'll show, in general it's not, because you have to think carefully about how symmetries act with the dynamics. So there are, so this is setting the stage, and I'll just tell you, since it's such a short talk, I'll just tell you essentially the results and illustrate their consequences. So, so what we'll do is think about starting in the ground state, so from free fermions and some Hamiltonian, we have some fill the lowest band, which is a band of some initial Hamiltonian hi, and then we'll time evolve, consider a quench where we time evolve under some other Hamiltonian. So when thinking about symmetry, there are two situations that one can think about. One is a sort of trivial case, where if you say, imagine that this hi had some symmetries which allowed us to have some topological invariant initially. Well, if we break those symmetries in HF, then clearly that topological invariant no longer makes any sense. It can change at later times, and so we wouldn't expect the topological invariant to stay fixed to whatever it was. So this would be completely different from the Chern number case, where the Chern number was fixed as a function of time. Here, just because we explicitly broke the symmetry, we've got no reason to expect the topological invariant to stay fixed. So that's what we refer to as explicit symmetry breaking. The thing that you can then ask is, well, what if the final Hamiltonian also has the same symmetry? So you started with a system with a certain symmetry. You now evolve under a Hamiltonian which still has that symmetry. Well, you might expect that symmetry would be preserved, but it turns out that it's not, in general. It can still be broken after the quench, and or certain symmetries can be broken after the quench, and those are symmetries which are so-called anti-unitary symmetries. So these are ones like time reversal symmetry, which have the feature that essentially they change I to minus I when you act in this way. And the basis of it comes down to this, that the time evolution operator, the action of the symmetry on the time evolution operator is to swap the sign of time. Okay? So what happens in this case is that if you have symmetries of this type, then even if the Hamiltonian preserves that symmetry initially and finally, then the mere fact that the Hamiltonian has changed in time will mean that the state of the system, psi of t, will no longer show that symmetry, meaning that it can't be viewed as the ground state of a Hamiltonian that has a given symmetry. So we refer to this as dynamically induced symmetry breaking, and it was something that surprised us, but turns out to be rather generic in thinking about the dynamics of the system. So this leads to this slightly confusing statement that what one thinks of as a topologically invariant actually becomes time varying even if the symmetries are respected, and it's because dynamically that symmetry is broken at later times. Okay, so that's the main point, but let me just talk about the consequences. Well, one could look for this just by doing the sort of block state tomography that Christoph Weitenberg's group has done to just extract the states across the Brillouin zone. But it turns out in one dimension, the time derivative of this CS1 is actually the current in the system. So by measuring particle flow or accumulation of particles at one end of the system, one can directly measure this, which is rather convenient. And one can check in explicit calculations for the SSH model or that in situations like this A3 case where the system has only protected by chiral symmetry, then the time dynamics is at later times is that this invariant changes in time. But in a case where you have several symmetries that protect, then the time evolution breaks two of these, but it leaves a particle hole symmetry that means that this stays invariant. So one can look at the dynamics of there are clear reasons why you get one sort of dynamics or another just based on these symmetry principles. The other thing that one can think about is what topological classification means out of equilibrium. In equilibrium, once it's topological, there are gapless edge states. And what we propose is that out of equilibrium, one can still think about this classification by looking at the entanglement spectrum, splitting the system into two pieces, and the eigenvalues of the Schmidt decomposition define an entanglement spectrum. It's known at equilibrium that this is gapless if the equilibrium spectrum is edge spectrum is gapless, but one can also track this out of equilibrium because we just have psi at t. And indeed, one can show that in the case where you break the symmetry that protects it, the entanglement spectrum quickly becomes gapped. In the other case, it stays gapless. So one has a meaningful topological classification out of equilibrium. So one can go through this in full detail for all of the different symmetry classes in one dimension, and one gets a prediction for how the equilibrium symmetry classification or topological classification changes to a non-equilibrium classification based on these rules, and one can test that this appears correctly in the dynamics of the entanglement spectrum. Okay, with that I'll just summarize that out of equilibrium, the so-called topological invariants can, in general, vary in time through this notion of dynamically induced symmetry breaking. So this has a consequence that there's no obstruction to changing the topology of the state dynamically, even if you respect the symmetries of the Hamiltonian. Just dynamically the symmetry can be broken. It also means on the downside that some things you might think a topology is insensitive to will be sensitive to noise. In 1D you can measure these time variations as a current, and we have this robust topological classification out of equilibrium where the bulk boundary correspondence applies to the entanglement spectrum. Although I've talked just about non-interacting fermions in one dimension, it holds also for interacting systems and disordered systems through this entanglement spectrum. Okay, with that I'll stop and I'll thank you for your attention.